Good afternoon. I'm Rachel, and the topic I will be presenting today is the use and physiology of HRV, or heart rate variability, in workload analysis. There have been a number of references used in this presentation, but the main article of reference is the study by Horsgraff entitled The Effect of Mental Stress on Heart Rate Variability and Blood Pressure During Computer Work. To start off, I want to say a little bit about myself and why I'm interested in this topic. I'm a biomedical engineer and have been working at a small medical device company for the past 5 years. Our focus is to make medical devices for point-of-injury care, such as the monitoring equipment that would be used in ambulances, helicopters, or brought on a military mission by field medics. We also do research and include an element of predictive medicine in our products. Predictive medicine is using all the information available to determine if or when a patient is about to crash or take a turn for the worst. Similar to how HRV can be used to quantify the stress for workload assessment, as was discussed in the multivariate workload evaluation class reading, we have used HRV in our predictive modeling to assess stress from an injury. Today I will be explaining a little about the physiology of HRV, then discuss a study which performed HRV analysis during a computer task, and finish with some thoughts and tips about performing HRV analysis. Now, I'm sure some of you started to skim a bit when the multivariate workload analysis article started naming off all these medical terms, and I don't really blame you, because the article didn't really delve into the details of what HRV really is, how it can be used, or when it is useful. Therefore, before getting back to the article, I will explain a little HRV physiology. To begin, the heart has its own intrinsic steady rate. However, signals sent from the brain by ways of hormones and nerves cause the heart rate to increase or decrease from this intrinsic rate. The amount of time it takes for signals to reach the heart, as well as the constantly changing signals from the brain, cause the time interval between each beat to become varied, as shown in the picture to the top right. The amount of difference is small, less than 150 milliseconds, and usually unperceivable without the use of ECG analysis. Because heart rate is completely out of conscious control, HRV provides a unique look into the autonomic nervous system, which is all the things your body does without you realizing they are going on. Heart rate variability can be measured in the time domain using standard deviation or by counting how many beat-to-beat differences were over a particular threshold, or HRV can be assessed in the frequency domain, where spectral analysis is used to determine the prevalence of frequencies within the ECG signal. Spectral analysis has the advantage of being able to separate the influences to those which slow down the heart, which show up as high-frequency components, and the influences which speed up the heart as lower-frequency components. Decreased HRV can indicate a lack of ability to respond to physiological variability and complexity, thus making the individual physiologically rigid and therefore more vulnerable or prone to health-related issues. Now that the physiology has been explained, we will move on to the article. As a reminder, the article reviewed for this presentation was titled The Effects of Mental Stress on Heart Rate Variability and Blood Pressure During Computer Work by a group led by Horsgraff. In this article, the authors investigated the ability to measure the effects of external mental stress during computer work. This article had two hypotheses. First, it hypothesized that there would be a decrease in HRV and an increase in blood pressure as a result of cognitive and emotional stress put on the subjects. It also hypothesized that if a physical task was combined with a mental stress, cardiovascular recovery may not occur if only the physical task is removed. The experiment was broken up into 3 sessions: an introductory, a stress, and a control session. The timing on each session was identical, with 4 work periods, as shown in the dark bars of the figure, followed by a 30-second break. At the end of each session was an 8-minute rest period, followed by a survey of the subject's experience of stress. During the introductory and stress sessions, the experimenter was unfriendly to their colleagues and neutral or strict towards the subject. Also during the first 2 sessions, there was a memory test which the subjects were shown a list of words at the beginning of the experiment and told to remember as many as possible and name off at the end of the experiment. These 2 sessions were also recorded. During the control session, the instructor was friendly and encouraging, and there was no memory test, and the session was not recorded. During the work periods of all 3 sessions, the subjects were instructed to key in the 6 digits as they appeared on a computer screen within 4 seconds, and all errors would be counted to determine a score. The results found that there were a significant difference between the stress and control sessions and the high frequency and the low to high frequency ratio components of HRV. Also, diastolic blood pressure was significantly lower in the control session. Exhaustion was the only stress condition indicated that was significantly higher during both the stress and control sessions than in the introductory session. There were no significant stress condition differences between the stress and control sessions. There also were no significant differences between the stress and control sessions in accuracy or physical workload. Lastly, they found that blood pressure decreased significantly during each session's rest period compared to the blood pressure taken during the work period. The study concluded the high-frequency components of HRV are affected by an increase in mental stress, which was induced in this experiment by the mannerisms of the instructor, the memory test, and the camera recording. They also found that HRV changes found did not correlate with physical exertion nor task accuracy because neither of those were significantly different between the stress and control sessions. Their other conclusion was that there was a significant cardiovascular recovery during the rest periods of each session, but that blood pressure did not recover to pre-experimental values within 4 minutes of rest. In this study, subtle differences between the stress and control sessions were captured through the use of HRV analysis, even though the subject's perception of stress and their accuracy did not differ between the 2 sessions. The influence on how the 2 sessions were carried out affected the subjects subconsciously, which would not have been apparent without the use of HRV analysis. This study showed how HRV can be used to gain a unique insight, and these changes in HRV, as discussed earlier, could lead to a clinically relevant conclusion. Furthermore, however, HRV should not be relied upon as the only measure used to evaluate or assess subjects. Using HRV as one of a number of measures, such as the method used in the multivariate workload analysis paper, which created an equation that included HRV as well as other measures, is a useful way to utilize the HRV results. To summarize what we have talked about today, first we discussed the physiology behind heart rate variability. Next, we discussed an article which used heart rate variability to assess mental stress while completing computer work that found that HRV changes did occur when mental stress increased. And lastly, we discussed the usefulness of HRV. Here are the references that I have used on this presentation. And I want to thank you all for listening to my presentation today.